All right, so there it is. There's the definition of dispersion, the separation of white light into the different colors of the rainbow based on different frequencies of light bending at different angles as they pass through different mediums, right? So many of you, I would imagine, if not all of you, are familiar with the Dark Side of the Moon cover, right? The whole Pink Floyd thing where they show the white light passing into the prism and it shows it separating, or you guys have probably seen some image like that before, right? We're going to take a look at that as to why that happens.
Well, what does that album cover have to do with that? Or the album name have to do with the album cover?
It's just what they chose. I don't know. You can ask Roger Waters.
Yeah.
Right. So ultimately what happens, what we know is that light is made up of different frequencies, right? And different wavelengths. All light travels at the same speed, right? All light travels at that 3 times 10 to the 8th meters per second. However, we see different colors because light has varying wavelengths and varying frequencies. And I'm talking like wavelengths that vary from half a mile to a mile long, like a radio wave, down to the like fraction of a millimeter when we talk about, say, like gamma rays. Okay, we can only see a very small portion of the what we call the electromagnetic spectrum. We can see red through violet, right? We basically can see 400 to 700 nanometers. That's the range of light that we're able to see. Okay. We know that higher frequency waves, or waves that have shorter wavelengths, bend more as they pass through a prism, right? So if I take white light and I was to send it into the prism, if you remember, what we do is we draw a normal that would be perpendicular to the surface. And with the idea that the higher frequency waves, the violet waves, are going to bend more. Now, as we go, I'm sorry, let me slide. As we go from air into the prism, right? The prism is going to have, you're going to move slower through the prism than through the air. Which, am I going to bend towards the normal or away from the normal? I'm going from fast to slow. Fast to slow towards the no, right? Well, what we know is that my violet light will bend more than my red light.
What's the dot?
That's my normal.
How is it your normal?
Because it's perpendicular to the surface. Remember, my normal is always perpendicular to the surface, right?
It's not perpendicular.
It's close enough.
It's supposed to be perpendicular.
Yes.
Okay.
And then as we pass from the prism back out into the air, we're going to go from slow to fast. So we're going to end up bending even more, kind of away back from where we were. But again, the violet ends up bending more than the red one does. So we get this separation of the color. Now, I only have the two extremes, right? In between there is where you would get your orange, yellow, blue, green, right? Your other colors of the rainbow.
Wait, so where did that like second D come from? The second right
What's second ray?
after the original thing.
What do you mean?
Someone says
The
it
black
is-
line going in is your white light.
The what?
The black line going in, your incident ray to the whole thing is your white light,
Yeah.
right? And that white light hits the prism and it separates a little bit into your red and your purple. And then as it exits, it separates even more.
Okay.
So violet's faster, like the fastest.
No, remember they're all the same speed, but violet has a higher frequency, has a shorter wavelength, right? Because if you think about, right, we know that the velocity of any wave, if we go back to our waves and sound unit, can be calculated by doing velocity as frequency times wavelength. The velocity for both of them is the same. But because violet has a higher frequency, it's going to have a shorter wavelength. And the higher the frequency light, the more it bends. So this isn't something I had always just kind of been like, all right, well, you just memorize that, right? Mrs. Fine Ice was telling me earlier that she knows a teacher that used to teach here and then ended up at Vernon Hills for a while, and is now retired. The way she does it is, if you think about a politician, a high frequency politician would be one that is going to shake a lot of babies and kiss a lot of hands, right? Reverse that. You're going to shake a lot of hands and kiss a lot of babies, right? Because of that, they get slowed down by the crowd, even more so than a low frequency politician that might shake a couple of hands and just move through the crowd, right? So the prism will slow down the violet quicker than it slows down, say, the red. That's why you get that dispersion. It's going to change its speed quicker. And really, that's just, we don't do any of the math that goes along with it. We don't do, oh, well, if it comes at this, then red will have this angle and violet have, no. I just need you to understand the idea that a prism is going to slow down the violet more than the red. And that's why we get that rainbow effect.
But you say slow down, but you also say they're the same speed.
Okay. You're right. I'm kind of mixing up the words a little bit. They are going to travel at the same speed, but it bends, the change happens more with the violet light than the red.
Because it's a higher frequency.
Yes.
He's shaking more hands,
Right? Violet is shaking more hands and kissing more babies.
So what color would that be of the shirt if it was like straight out?
What's that? Oh, the shirt's just got it completely wrong.
Oh,
So the whole album cover's got it wrong. Well, and this isn't even the album cover. The album cover just has like one white beam coming in and separating into one rainbow.
yeah, it's kind of sick. It's a good album.
Right. So this idea of how these light rays bend, right? What I want to do is I want to look at how this affects, or when we have lenses, how does this relate to a lens? Ultimately, the first lens that we're going to look at is going to be what we call a converging lens. So just like with mirrors, we've got lenses that are going to either bring the light beams together or spread them out. Okay. So when we are looking at a converging lens, we're looking at one that is going to bring our light beams together. That lens seriously? is going to look something like this. And what we want to do is we want to look at 3 light beams that are going to come in parallel. One of them is going to hit our triangular prism. One is going to come straight through the middle of our rectangular prism. And one is going to go through our second. It doesn't really matter. I'm just making a new color to distinguish it from the. At this point, we're just looking at light. It doesn't matter what color it is. Right, and now what we need to do is we're going to look at how this light is going to behave as it passes through the different areas. Now, here's what's good, right? When we pass through a rectangular prism, as long as we pass perpendicular, we're just going to pass right through, right? It's going to change the speed of my light, but it's not going to bend it at all. All right, so that's just going to pass right through. I need to actually, we're going to want that to be more in the middle there. And then for this one, we need to right, and let's make my normal here. Once again, fast and slow, we're going to go towards the normal.
Is there any instance where you go away from the normal?
If we go from slow to fast. And we're going to redraw a new normal. And my new normal here. And now we're going from slow to fast, so we're going to go away from the normal. And you'll see that it brings all of my rays, regardless of where I pass through, to one point. That is the focal point for my lens. And we can actually see that. All right, I'm going to stop sharing my screen here for a moment. You guys need a second before I do that? All right, we good? All right, we're going to stop sharing my screen. I'm going to move this over so that you guys can see this. You're going to want to focus on my, there we go. All right, you guys can see the laser, right? You can see all those beams. And what I have is I have a I don't know how well you guys can see this, but I'll show it to you again when the lights are on. I have a converging lens. Watch what happens when I put it into or in the way of these parallel lines. You can see, and it's not perfect. This isn't, I mean, this is a cheap lens, but it gets all of them to focus at one point. Right, all of mine come in parallel and they all end up focusing right about there. Like I said, this is kind of a cheap lens. It's not exactly perfect. A really, really good lens has all of them focused at one point on there. And it probably doesn't help that I'm not perfectly perpendicular on there. That might help a little bit too. But you get the idea, right? All of them coming together. Now, in order to not go like turn off the lights, turn on the lights, turn off the lights, stop screen, share screen, I'm going to show you guys the diverging lens as well, so that you guys can see what it does, right? If I put that in between there, you can see that it takes those light beams and instead of bringing them together, it actually causes them to separate out. Right? It causes the rays to diverge instead of converge. And we're going to look at that one next as to what that looks like and why that happens. All right, let me bring all of this back. I'm going to show you guys really quickly diverging lens, and then that'll be the end of it. Go back to sharing my screen. Uh-oh. Why did that happen? Okay. All right, not perfect, but it will work. All right, so we're going to do the same thing. We're going to take these three parallel rays and we're going to pass them through. Right, and we're going to have to go through the same steps, right? We're going to create our normals. And do one here. Once again, we are going fast to slow, so we're going to go in both cases. We're going to go towards the normal. And towards the normal. Create new normals. And again, now we are going from slow to fast. So we're going to go away from the normal. And that's how we end up with the diverging rays. Now, if we connect those lines back, once again, we get where our focal point is. And you'll see that for a diverging lens, our focal point is actually on the side where the incident rays are. That's a diverging lens, and this is a converging lens. Go back and give you that picture again. And what we're going to do, because we're going to be doing ray diagrams with lenses just like we did with mirrors, there's a shortcut. You don't have to draw 3 different ray diagrams for each lens, and like it's not, it gets a little bit easier. There's a quicker way to do this. We're going to go over that the next time we meet. Any questions on dispersion, lenses? Xavier?
So is it possible that it could be reversed where it's going away from the normal first and then going towards the second?
You would need to be passing from a slow material to a lens that is made up of a faster material than your.
I would say, like, would you see that?
I would imagine there's probably a way to do it, but I'm not like you would need, like I would have to look at, I don't remember what the different, but maybe if you had, like if you had a special, like a lens in water that had a lower N value than water does, then I suppose you could. I don't know what that would look like though. As far as like what it would. I mean, I suppose you could sit down and make the ray diagram for it. I just don't know.
Yeah.
Off the top of my head. Right, and really what we should do here is.
Wait, how did the focal point go from there to there?
Yeah, right? Like, why did you just extend
What's that?
why did you like extend the lines over the other?
To show you guys where the focal point is.
The focal point was to the right.
That was
Well, but
converged.
that was when it was for a converging lens,
Oh,
right? We should probably dot these lines.
Oh.
Right, because the light's not actually going towards those focal points. It just looks like it's coming from the focal point there. Any questions on dispersion or lenses or?
how does a one-way mirror work?
How does a one-way mirror work?
Yeah, or one-way glass.
It is about the like where you have a film, like it's a special type of film.
Okay, isn't there like all those sheets, like something in the glass on like one side, but, like maybe
Yeah.
they reflect back at you.
Right. It's about the reflect, but it also like that also is kind of, so if you ever like one of the ways to kind of think about it, if you ever stand inside your house at night with the lights on and you see your reflection, but you really don't see outside, and the people that are outside will see into the house,
Oh,
right? It's about where you get, where the light is relative to the reflective surface.
gotcha.
right? If you ever notice that, like standing inside, if your light's on, like you'll see basically your reflections, but people outside, that's why like if you're, you can be inside with your shades open as long as it's darker in your house than outside. But the moment it gets dark out and you've got lights on in your house, now people see in your windows.
Okay.
All right, well, if there are no other questions, then you're going to want to look at pages 24 and 25 in your packet. That's the assignment for today. You have the next 12 minutes. You can probably knock it off before the period even ends. Otherwise, enjoy the rest of your day. Take care of yourselves. And if you've got any AP exams before I see you guys again, good luck on those.
All right, thank you.
Thank you. Have a good one. Yes.
I'm not gonna be here on Friday.
You'll be missed.
Like, what do we need to do? Do you know what we're gonna do?
Are we